Okay. So let's get started.
I do the noise here.
Sure. Okay, so this is the last session of the course. And yesterday we proved this. We gave this the proof, precise proof of this result in a rank. That then later gives you reference. We realized that it also, the proof also works on every hypersurface, right? That has a lower bound on its density. So we are in Rn+1. We have a set. I put it surface like this because it's not very important. Its regularity or anything. Just probably that it has finite perimeter to integrate, so that these integrals make sense. But doesn't matter. Let's think that it's a hypersurface. It may be C infinity, but of course it may fall if it falls a lot. If it falls a lot, when you take even if it's analytic, when you take a point here and you take a ball of radius, an ambient ball of radius rho, maybe the perimeter is super large. That's fine. That's fine. Okay, that's fine. The problem would be that it's very small, and this in dimension 2, maybe you don't see it, but in dimension 3, right? If you have a very thin, in dimension 3, if you have a very thin cigar like this, correct? It will have very small perimeter, right? It can have very small perimeter. Is that correct? Yes, right? Because the size here, it can be of any order, and this will be the radius. But you want it to be comparable to r to the n. So if r is very large, r is much smaller than r to the n, you see? So that wouldn't be good. So this would be the enemy for r large, you see? You see, r large, this is r, this is of order 1. What is the perimeter of this cigar? Is these balls are, these spheres are of radius 1, and this is r. So the perimeter is of order. This perimeter here is of order r, or rho. Sorry, rho. And this you would like it to be larger than rho to the n, but this is impossible if rho is large. So if rho is large, this is the enemy. This type of cigar. Okay. And now we are going to kill this enemy for the objects that we care about: minimal surfaces and non-linear and non-local minimal surfaces. So this is the next section, right? 5. Density. By the way, today we already we will scan this, and you can put it on the web, or you can. But it's 300 euros. But they work a lot all the week, huh? Because to make it readable, okay? Okay, so this is this section. We are going to prove in all detail the density estimate in the local case. I will tell you that in the non-local case, I will give you a reference. The proof is the same, and then we will apply it to have this Sobolev inequality on non-local minimal surfaces. So this is the density estimate. Theorem 8, density estimate. Both for same proof and everything, and same statement, both for minimal surfaces. Minimizing minimal surfaces. We will do it in this case. and non-local minimal surfaces. Both for local and non-local minimizing minimal surfaces. You can prove it also for non-minimizers in the local case. In the non-local case, we believe that it's also true, but I think it's true, but it's not written anywhere. So, but let's just care about for the moment about minimizing, as I told you, that it's the variational setting from yesterday of Caffarelli, Roquejoffre, Savin, right? And it says simply, let's write it below, if the minimizing surface, boundary of E in B1, recall that we have E is an open set in Rn plus 1. Same setting as here, and N is going to be the surface, our surface is going to be the boundary of the open set. Okay? If the minimizing surface in B1 passes through the origin, now we should call it capital N. You see, the capital N from yesterday. That's why I changed from small n to capital N. In this case, capital N is n plus 1, small n plus 1. Passes through, so I'm following notation and being consistent with notation from yesterday, through the origin. Because you have to imagine that you have this ball. Of course, I can have a minimal surface that passes like this, and it has very small perimeter inside the ball. But the point is to pass through the origin. So if it passes through the origin, these things like this will be forbidden. And the reason will be the following. If it passes through the origin, that is, the origin belongs to the boundary of E. This would be the set E here. Then the measure inside the ball of the set E is larger or equal than a constant, a universal constant, which is positive, that the only depends on n and alpha, and the complement the same, because you can always switch E with E complement. E and E complement, there is no choice, right? Because their boundary is the same. So we just need to prove one of these two. And this is the statement, okay? This is the statement. And this in the local case, I don't know who proved this for the first time. Sometimes it's rarely written, but because it's an old result, right? But let's make the proof in the local case. And, okay, so proof in the local case. And in the non-local, it's exactly the same. The local case, non-local is the same. And you can find it very well written. Is the same, and C, Caffarelli, Roquejoffre, Savin, okay? And the only thing is that, as you will see, we will use a Sobolev inequality. The only difference is that we will use a Sobolev inequality, but we have the fractional Sobolev inequality in, so this will use the fractional Sobolev inequality in R capital N. That we have it from here, not on the hypersurface. You will see that I will apply Sobolev inequality in ambient space. So we have it from theorem proposition 4. And this is the only change. But if not, the proof is the same. So how does it go? Well, it goes like this. I wrote here by contradiction, but there is no need to be contradiction. So I keep it here because it's not wrong. But I just make a drawing. Well, I could take this drawing, but let's make another one. Here is the origin. This would be the set, say, E inside here, okay? And we take this is 1. Then we will take half the ball. So this is 1/2, this is 1, And now we will take any radius, right? Any radius, and we will look at this set. So now I take any radius between 1 and 1/2, r between 1/2 and 1, sorry, 1/2 and 1, and I will have this set here that I call V of r, and the volume. No, the set I will call it capital. Well, it's not very good notation, but let's call it V sub r. V sub r. And then its boundary, it has two parts. This one here, that I will call AR, and this one here, that is part of the boundary of the minimal surface, that we will call ER. Right? And then the other is very, very simple. You will see that very, very simple. And then we use the Sobolev inequality. So for characteristic functions. So Sobolev for characteristic functions. For characteristic functions, we know in this case the characteristic function of VR. We know that this is the same as the isoperimetric inequality that we proved, and this tells us that the with a universal constant, all the constants here, it will just depend on n. Later it will depend on n and alpha, capital N, sorry. The volume to the power n minus 1, capital N minus 1 over capital N is less or equal with a constant than the perimeter. The perimeter, the volume. The volume yes, let's use this notation. And I use this Savin, sorry, make it shorter. Yes. Like this. Yeah, let's use this one. Here it will be written a little different, but you will understand. Let's keep this notation. It's less than the perimeter of this set here. It's an open set. It's an open set in Rn, capital N. And the boundary, so the boundary of here. And the rescaling is good, right? N minus 1 over n, yes. And the boundary of ER has two parts, the one of ER and the one of A. But you see, now we will use minimality. So here we use the Sobolev inequality, here, first ingredient. And now we use the second ingredient, that it's a minimal surface, a minimizing minimality. And minimality implies, you see, you look at this picture and the plateau problem, wherever you want, for instance, in V1 or in V1/2. Let's think first of V1/2. This is a minimizing minimal surface in orange, and this is another one, the ball in yellow, that have the same boundary values on the boundary of V1/2. Since this guy is minimizing, the length of orange must be smaller than the length of yellow. Or you can argue in the V1 if you want, and the remaining thing will be the yellow with the white and the orange with the white, but the whites will be common and will simplify, okay? So minimality immediately gives that ER is less or equal than AR. And this part, so in the fractional case, this is fine, it's the same. Okay, we have this arithmetic. In this part here, you will have to work out a little like yesterday, like what I did yesterday, and that's why I did it yesterday. So now exercise, like yesterday, that thing of this decomposing a set in all the disjoint parts, outside, inside, and all that stuff. Right? Exercise. Do this in the do it in the non-local case. But before doing it, start with isoperimetric, because the isoperimetric will tell you which interactions appear, and then you will see what you need to do, and it will fit. Okay? And if not, it's in Caffarelli from Savin. So here we have now 2 times AR. But AR, like yesterday, remember, like in the proof of the Michael-Simon, again the same thing. AR is the derivative with respect to R of VR. So again, we come back to a very similar argument as in the proof of the Michael-Simon Sobolev inequality, an OD. But this is a nonlinear. In the Michael-Simon, it was a linear OD, remember, non-homogeneous, and we integrated it with the variation of constants. Allard, that was the Allard tree, very clever with that exponential of the primitive, remember? It was a linear, non-homogeneous equation. So Michael-Simon, so this is a nonlinear ODE, and this Caffarelli always emphasizes this, that it is nonlinear thanks to the Sobolev inequality, and this, and then thanks to nonlinearity, now we will see a fact, an extinction fact. You will see now why I say extinction. Huh? Instead, in the Michael-Simon, since it was a linear, nothing dies. In a linear OD, the existence is for all time, nothing dies. But here something will die, you will see in a second. Versus, let me write this, versus linear, non-homogeneous. Well, this is not important what I'm saying here. Huh? It's just because I see in this course, I see you put everything together and you see these differences and these similarities. Versus linear, non-homogeneous OD for Michael-Simon inequality. Okay, but this is lateral. So now I just have to integrate this OD and we are done. Let's do it, right? Let's do it. We have a constant. The constants change, but let me call them always C. They are positive constants. And then I have here VR to the power 1 over n minus 1 dr of VR, right? Is that correct? Yes, 1 over n minus 1, and therefore this is the derivative of VR to the power 1 over n multiplied by n. Doesn't matter the constants, I don't care about the constants. And therefore, now if I integrate C over n between 1/2 and 1, dr, it will be smaller than integrating 1/2, 1, C over n is the derivative of this, but this integral is trivial, and this one is also trivial. It's C over 2n, C over 2n, and this is V at 1 over n, minus V 1/2 and 1 over n. And now what you see, therefore, is that this volume is less or equal at 1/2, is smaller. For sure it is smaller. This is trivial. This is trivial. For sure it's smaller than V1. But now we have minus a universal constant. And therefore, now if you want, we are doing by contradiction. If this was 0, if this is small enough, is universally small enough, then this is negative, and therefore, in fact, this must be 0. Then V 1/2 must be 0, and this means that this set is empty almost everywhere, and this means in the measure theory sense that the surface doesn't pass through the origin because this is empty. Okay. And hence the origin is not a regular point or whatever of the reduced boundary. Here, I don't want to get into details like topological or geometric detail, measure theory, geometrical details. This is the essence of the thing. and hence zero does not belong contradiction. So conclusion, V1 is universally large. So conclusion, it's what we wanted to prove. V1, which is exactly the measure of the set intersecting with V1, right? It's what we wanted, right? The measure of the set is bigger or equal than a universal constant. Very simple, very nice argument, you see? And the extinction time is the thing that is telling you that since the ODE is non-linear, the existence for this ODE, if this initial value is small, it will not go for more time than 1/2. Well, time is like radius, okay? This is like the extinction, you see? This will never happen for a linear. Okay. And now we can continue upstairs, downstairs. And now, why do we get that? And so now from theorem 8, now we are going to use both in the local and the non-local. We are going to use the relative isoperimetric inequality. It's something that we have not done, but we have done the isoperimetric inequality. So the relative local or non-local or fractional isoperimetric inequality simply says that if you have B1 and a set contained in B1, but maybe not containing the origin, an open set, 0 may belong to the boundary of E or not, or not. I don't assume anything now compared to before, okay? So I see this picture here, and this is E here. Then it tells you the perimeter of E relative to the unit ball, which simply means, oh yeah, we spoke about, no, this is important, because yesterday we spoke about relative fractional perimeter. It was not so easy, remember? Interaction of this with this with that with that, and we forgot one interaction, outside, because it was infinite, remember? So, and how did we call it in the non-local case? I think I call it relative perimeter alpha of the set E relative to B1, right? I call it like this. So let's use this notation and understand that if alpha equals 1, I'm in the local case, okay? Alpha equals 1, I'm in the local case. So the relative isoperimetric inequality says that this is larger or equal than a universal constant times the minimum of the two areas to the powers that as you need to rescale the powers, okay? So the area of EB1 to the power, now there is a power which is fractional, right? What is the dimension of this? This is n minus alpha, right? In dimension, for alpha equals 1 is n minus 1, right? N minus 1, correct? Yes, n minus alpha. And this is of dimension n, so n minus alpha over n, and the complement. How do you prove this? I don't know if the proof that we did the first day, my proof of the isoperimetric, has been adapted to this. I'm not sure, but let's not waste time now. So, of course, if this guy is very small, then the perimeter is very small. So what you need is that both these and these and these have some size, and then the perimeter will have some size. Now, using theorem 8, and this, we deduce that no. Look at proposition 4. Look at proposition, now there is a mixture. Look at proposition 4. Now what I want to do is the fractional case. Now I want to do the fractional case because I want to prove proposition 4 for minimal, non-local minimal surfaces. But condition 4 is not for the fractional perimeter inside the ball. It is for the classical perimeter. So I'm not doing this, sorry. I think it was well written here. It's well written here. Yeah, the perimeter, the usual perimeter, relative, local. I'm going to use the local isoperimetric inequality within a non-local framework, but I have the right. The perimeter of E inside the unit ball, it is larger than this. Now I'm fine. Now I'm fine. And this, no. This is the relative is true in all the cases. Okay, but now assume that the origin is on the boundary, and this origin is going to be that point x0. You see that x0 is in M. So I have this surface M, which is the boundary of E. I take any point on the surface. I'm checking condition 4. I take any point on the surface. I call it 0. I make these balls. I make this argument. First, I do it with B1, and then I rescale. By rescaling, you can pass from B1 to B raw because everything is rescaling variant. And if you rescale a non-local minimal surface, still a non-local minimal surfaces. So assume that the origin is on the boundary, and use theorem 8 that, of course, requires that the origin is on the boundary, and you get that these two sets, I wrote them good, yes, same order, have some density, so this has some density. Assume that this, we get that M, which is the boundary V, in B1 center at x0 is greater or equal than a constant. Now you rescale, and therefore after rescale, you get 4. So corollary, get 4. For every, you do it at every scale. So corollary, did I write it as a corollary or as a corollary here? Corollary, and this was the starting point of this paper that I did with Matteo Cozzi, who is now in Milan, and it's called a gradient estimate that I will describe a little more now. And it was published in 2019. Okay, and it says the fractional Sobolev inequality 5 for S. There is one parameter S here, and now there will be another fractional parameter for S. So I'm speaking about, and V. So I'm speaking that I'm applying, I'm getting Sobolev inequality on the surface, for the norm, for the semi-norm WSB, holds on every minimizing non-local, alpha non-local, non-local alpha, minimal alpha, alpha non-local means that it is a non-local minimal surface with kernel alpha. And this holds for every alpha. The point is that this holds for every alpha in 0, 1 and every S in 0, 1, independent, no relation between them. Okay? And there is nothing, we have proved this. Because this, with the help of resist, we only needed the lower bound on the density, and the isoperimetric inequality, relative isoperimetric inequality tells us instead of the perimeter bound by below measures, both measures, it will be enough. It will be enough. And how do we bound both measures? We bound both measures with this argument using, but adapted to the fractional case, which is the same rule. Okay? So now that we have this corollary, it's now what I can describe for you in the next section, a little this work with Matteo Cozzi, okay? That it is, so now section 6, application 1, so in the rest of the day, in the hour, I would like to make 2 applications. Application 1, I should try to go a little quicker and don't speak so much. Application 1 of fractional Michael-Simon inequalities, a gradient estimate for non-local minimal graphs. So let me state it, and then we try to, and then I describe you a little the proof, because it mixes very important ingredients that you can use in many other problems, okay? In many problems. This is very important because it's the Georgi Nash-Moser technique in a way. Yes. So theorem 10. Do I need notation? No, I don't need notation. You see, that's good. Theorem 10. So this is the paper with Matteo, 2019. Theorem says. You give me a function from Rm to R, and I'm going to look at its graph, or the subgraph. And I'm going to be again in Rm plus 1, and I'm going to look at the subgraph, xn plus 1 less than u of x prime. So it's the subgraph, right? So we have here Rm, but we are working in Rm plus 1, that you should think that it's like the R capital N, and we have this function, all right? Here we have the point x prime, we have this function, u of x prime, and we have this function, and this is the surface, and this is the set E is below, and this is the surface, okay? So this is contained in Rn plus 1, it is open, and we need n to be bigger or equal to 1, and we will have a parameter alpha between 0 and 1. So assume if the boundary of E is a non-local alpha minimal surface in a ball, in a cylinder. So now I will take here a ball, I will take here a ball, and I will make this cylinder, right? Take a ball, and I will make this cylinder. And if this is an alpha minimal, minimizing alpha minimal surface, but don't worry about minimizing, the graphs are always minimizing, so don't worry about that. Then, or if not, yes. Then, first, and this was new, this was not new, u is infinity, is smooth in half the ball, and its gradient, it's a gradient bound. Its gradient is bounded in the large ball, even in the large ball, by a constant that depends only on n and alpha. And then this expression, look, 1 plus the oscillation. Well, you always have to think that planes are minimal surfaces. So you see, this plane has a very big slope, very big. It has very big slope, but it also has very big oscillation. So I will bound the L infinity norm of the gradient by the L infinity norm of the function. So the oscillation in dr prime, this means ball in R. of u divided by r, you can prove it for r equals 1. And here you have an exponent and n plus 1 plus alpha, and this is the statement, okay? So now, I think I can erase. Now I'll tell you the main ideas of the proof. But I can also erase the other thing. So, is there any question with the statement? I think it's clear, right? So the smoothness of non-local minimal graphs was only known in dimensions 1, n equals 1 and n equals 2 by results of Savin and Baldinocci. Savin, Baldinocci, and Figali. 2 papers. They put them together. Smoothness was only known before for n. So that's why we were quite happy. We were happy with this, okay, with this result, because this was not even known. In fact, once you prove that u is, the gradient of u is bounded, like in minimal surfaces, if you know a little of minimal surfaces, you will see that once you prove that if you write the minimal surface equation for graphs, it is this equation. Once you prove that the gradient, this is a divergent form equation, but it's quasi-linear. Once you prove that the gradient is bounded, you can look at these as coefficients, like in Moritz-Stock, and they will be uniformly elliptic. And then you are saved. So once a minimal surface is Lipschitz, you can prove that it's infinity. Thanks to the De Giorgi-Nash-Moser, this is perhaps the most important result and something that developed the theory of PDEs in the 20th century, right? And De Giorgi and Nash should have got the Fields Medal for this, but they did it independently. And then it is said that and they were under 40. It is said that they didn't get the Fields Medal because they did it at the same time independently. But they should have, because De Giorgi. So what was the point? The point is, if you have a divergent form equation with coefficients which are uniformly elliptic, but you don't know if they are continuous, just bounded, measurable, but uniformly elliptic below and above, then you would like to prove that the solution is Holder continuous. Well, in fact, you will apply to the derivatives of u, not to the u in the minimal surface equation, but that's technicality. You just trust me. And then you will be able to prove, when you apply to the derivatives, you have to differentiate this equation. You apply to the derivative, you are able to prove that the derivatives are C alpha. So the solution is not only C1, but it is C1 alpha. And then you repeat the process, but these coefficients are C alpha. And then you just use Schauder theory, which is classical, okay? All this you have to learn a little in the book of Gilbert and Schrödinger, for instance, okay? But the key point was to do the De Giorgi-Nash-Moser. And then Moser came later and gave a third proof that I will use today, the one of Moser. But the 3 of them are very useful and very good to have 3 different proofs. Non-local in one problem, one will be better, another problem, another can be better, okay? Now, we don't have time, but now the non-local minimal surface equation for graphs looks like similar like this, but of course it is a fractional, so there will be an integral, and the energy behind it will be a double integral. But here there will be a quasi-linear function of a nonlinear function of those guys. And here there will be more those guys, okay? And then dy, and this will be 0 for every x on the boundary of E. The equation will look like something like this, okay? You can find it in my paper with Matteo, for instance. And this is like a fractional quasi-linear, right? Quasi-linear. Once you know that the solution, once you know that the gradient of u is bounded, then you can do the same things, and you can look at this equation like a linear equation, fractional linear equation with coefficients, and then do the fractional. And now, so okay, so let me write a little bit these things. Later, I want to yes, we go to the local. So gradient estimate. So gradient estimate, it allows both in the local and non-local, doesn't matter. Local and non-local, it allows to the gradient estimate. It allows to work with to get linear local or non-local divergence form equation for the derivatives of u, and uniformly elliptic divergence form, uniformly elliptic, but with bounded measurable coefficients only. You don't know if they are continuous. Then in the local case, you apply the theory of the Georgi-Nash-Moser. And the first person who did this in the non-local case, and this person will correct me if I'm wrong, was Moritz, right? Yes? Yes. Good. And you did the Nash, no? The Georgi, no? You did the Moser, probably. Yes. 3 proofs, very interesting. You can even read the paper of Nash. It's very readable and not too long. You can read its paper. Or you can read, no, his paper, no. Okay, I'll tell you the good references. This you have to read a paper by Phelps and Struck that is called Proof of the Harnack Inequality Using the Old Ideas of Nash. Beautiful, super easy to read. The Georgi, you have to read the lecture notes of Caffarelli and Vasser. Lecture notes. Super nice to understand, and there are several versions of the lecture notes. Get the good one, or look at both versions. And the Moser, you can read it in Gilbert-Rudinger, right? For instance, for the local case, or in many other places. In the non-local case, the first time this was done was by Moritz Kassmann. First time using the Moser theory, the Moser method. Okay, now I lost a lot of time. I'll have to stay half an hour. This we can erase now. We can make the coffee break here, and I don't expect that. Okay. With Matteo, we are also going to use the Moser method. I will say later. But for another thing, to get the gradient estimate. So this is, once you have the gradient estimate, you have a smoothness. So all this story is about this. So all this story is to tell you that once you have the gradient estimate, you have infinity. Okay? Good. Thanks to this is from here, the Georgi-Nash-Moser. Okay. Let me say that. Okay, so let's go back to the gradient estimate now. So now we come back to prove to the gradient estimate. And let me tell you, that in the local case, this is an odd result. In the local case, this was first proved by Finn when n is equals to 2, and you have a surface in R3, Finn, 1963. And then n greater or equal than 3, Bombieri, De Giorgi, and Miranda. Bombieri, De Giorgi. Miranda, in a very good year for minimal surfaces, which is 69. 69 is like, well, it's a nice number. But it is, there is this, I think there is the Simon's paper on the cones, the classification of cones, well, several of them, okay? So all this development and bloom of minimal surfaces and concluding the theory is these years, 69, 70. Okay, so that's it. So now, main ideas of the proof of theorem 10, okay? The paper is long and it is super technical. I was very glad you remember, Mark. You were still in Barcelona or no? No. With what? Yeah, no. It was. You left in 2016.
Yeah.
So, yeah, I think 1 year you interacted. So Matteo is super good technically with all the fractional stuff that I wouldn't know how to do, and this was super good. But the ideas for the paper are very strong and very nice, very natural. So after some weeks, I was, well, more than him because of the experience. I was convinced that it had to work, okay? But then it's very technical, but it's nice and it's clean. But the ideas are these. Let's do first the local case. And I will tell you some things that the geometers know perfectly, but the analysts, maybe not so much. Here, if you are an analyst, again, you can go to well, you can go to many places. The book of coding and Minicozzi, I like it very much, okay? For an analyst to learn the first chapters, to learn a little geometry, right? Riemannian geometry and these things. If not in my lectures notes with Giorgio Poghesi that I already mentioned, you can also learn a little about these things, just knowing very little geometry, say. So what I want to say in the local case. So you have a minimal surface, and this is the mean curvature is the first variation of perimeter, right? I need to write height of perimeter. Now you make the second variation of perimeter. Because, for instance, if your surface is minimizing, the second variation will be non-negative definite. A non-negative definite quadratic form. And that can be very useful, right? To work with and to use. So you make the second variation. To make the second variation is to make the same thing as the linearization. The linearization of h of the first variation at your particular minimal surface. And this will be the second variation of perimeter. And this is a quadratic form associated to an operator that is very important, and it's called the Jacobi operator. And I tell you now what it is, the Jacobi operator. And I guess, but the geometers will tell me the Jacobi comes from the study of geodesics, right? Like the Jacobi fields in geodesics, because you have a geodesic that minimizes length in a Riemannian manifold, and you want to know, well, you know that it's a critical point because it solves the ODE, but then you want to know if it really minimizes length or maybe not, right? So you have to look at the second variation. And the Jacobi operator, we will call it capital G. It will act on a function. For instance, think of graphs. U is your graph, V will be a perturbation, and then it is always, but not necessarily a graph. I'm not speaking about graphs. I didn't write it anywhere. It is the Laplace-Beltrami operator on the surface. Of course, let me write it like this, but later I will amend Laplace-Beltrami, which is just Laplace for us, plus a squared applied to V. This I will call it like this. V will be a function defined on the surface with compact support, probably, and where a squared is the second fundamental, the square of the second fundamental form, square of second fundamental form, which is the same as the sum of the squares of the principal curvatures. Where am I now? Am I in Rn? In Rn plus 1. It's a surface, dimension n in Rn plus 1. So this is correct. The principal curvature. Okay? And this is a delicate operator because this operator here is negative definite because it's not minus Laplace, it's Laplace, and this term here is positive definite. So they are fighting with each other. And if the minimal surface is minimizing, or even more generally, the stable minimal surface, this is by definition, this will be the same as knowing that the Jacobi operator is minus Jacobi is greater or equal than 0. Sometimes I prefer to write it like this, okay? And this says that the Laplace beats, minus Laplace beats a squared, okay? Minus Laplace is stronger than a squared. What else? Okay, now translations. This is your surface. You translate it, and you have this not new surface, not an integral, and it is still a minimal surface. If this is a minimal surface, this is a minimal surface. So H equals, this is something very interesting, very important what I'm telling you, but works for all equations. I'm trying to tell you tools that work for all equations. If you have an equation that is invariant by translations, is invariant under translations, or rotations, but in this case we are doing, later we will do rotations, but for the moment we are doing invariant by under translations. This means that when you differentiate, there is a guy, a specific guy, given by translations, the generator of translations, that is in the kernel of the linearization. Which is in the kernel. So the infinitesimal, say, generator of translations is in the kernel of the Jacobi operator of the linearization of the equation, which is the Jacobi operator. What is the kernel of translations? Well, the translations, this is the infinitesimal, the vector field that generates translations. But when you write everything on minimal surfaces, on surfaces, we always write all the expressions on the normal. So we perturb the surfaces. We always perturb the surfaces. When we write a quadratic form of this, we take the surface and we perturb it. Now, is this correct? Yes. With a test function times the normal to the surface. So I will take a point in the surface and I will perturb it like this, right? Always in the normal layer. And therefore, you have to make, you see, if the surface is like this, the normal is like that, and when you translate it, it's itself. It doesn't change. So there is nothing in the kernel. Nothing in the kernel, because if you translate something horizontal, right, you don't, it's the same. So you have to make the scalar product of E with the normal, right? With the normal. So this is saying This is saying that the normal times ek, which is the kth component of the normal k plus 1 to n plus 1, because there are n plus 1 directions, is a solution of the Jacobi equation. Satisfies 0 Jacobi of mu kn. Okay, this is trivial for geometers, but I'm sorry for this means that it satisfies this on the surface. But this, of course, you can also do computing. So it's an exercise, and you will see it in the books. You will see it in the books, in some books that you compute using Riemannian tangential derivatives, or the tangential derivatives of Bombieri de Giorgi-Giusti. If you are an analyst and you say, no, I don't want to use so much geometry, Riemannian geometry, whatever, you can compute this. But I told you the general idea behind that works for every equation. You will have this, okay? Okay, so this is what I want to say in the local, and now let's make a parallel picture of this in the non-local to see how all this looks, right? How all this looks. Let us keep the estimate. Let us keep the estimate and let us write here. Yes. So the non-local case. So what is the Jacobi operator? The Jacobi operator, well, how, and you can tell me, how will you compute it? Well, well, the equation is invariant by translations, and then you have to see how the non-local curvature changes under all directions, tangential and normal. And that's a lemma. I will mention before later the lemma when you will see where does it appear. But it has this form. So let's call it J alpha of V. And it is an operator L of orders of with index 1 plus alpha over 2. I'll tell you in a second what it is. Plus C squared 1 plus alpha over 2 at x applied to the function V. And from now on, I will call it S, and this I will call it S. So V, so I will always have that S is a parameter 1 plus alpha over 2. Alpha is in between 0 and 1, and therefore S is in between 1/2 and 1. So now I will have this range appearing, and these operators are L. I have it written here for 1 plus alpha over 2. Because let us fix in our mind that alpha is my non-local minimal surface is alpha, corresponds to alpha. So this operator, it's an integral. It's like a fractional Laplacian with the other sign. This will be the analog of Laplace, which is minus Laplace. Okay, minus Laplace. So, and fractional here. So that's why instead of v of x minus v of y, I write v of y minus v of x. Here, the usual kernel, n plus 1, small n plus 1 plus alpha, dvy. And the integral is in m. So, and this is the ambient distance. So I'm integrating on a manifold, but with the ambient distance. Here there is something that geometrically is not very nice. Nobody says that, pretty much. That is, well, many things will be very nice. But what is the main, one of the main, let me just say this, let me put it in another column. What is one of the nice things about the fractional Laplacians that maybe some of you are not aware if you are starting with this stuff? The nice thing is that when you make the fractional Laplacian and you compose it with another fractional Laplacian, it gives you this other fractional Laplacian, the semi-group property, right? That you prove it, for instance, doing Fourier transform or in other ways, okay? This happens for the fractional Laplacian in Rn. This will not happen for this guy. Because look at the geometry of n, you don't know what it is, okay? It's a minimal surface or non-local minimal surface, but you cannot hope for this, okay? So this will not hold, in general, will not hold for L. Instead, there is a very recent paper of Joaquim Serra and his students where they clearly write in a very nice way with three different formulations: heat kernels, spectral decomposition, and another one that I don't remember now, maybe the extension. What is the fractional Laplace operator on any manifold, or at least any hypersurface? With hypersurfaces, but I think even manifolds, okay? Intrinsic with the semi-group property, and that the expression using the heat kernel is not so complicated, okay? So for this, you can see, I'm not sure if it's in archive already, but I think so, something Joaquim Serra and collaborators, and very recent in archive, or if not, you will have to wait we have to wait 2 weeks. Okay? But this is what we get. This is what we get with non-local minimal surfaces. And then C square, if you are a geometer, and you like this a little, you say, what is going to be the second fundamental form, right? Fractional. This should be the second fundamental form, but the fractional version. It is a square also. And this is this expression, look. This is this expression at the point x. X is on m, of course. It's the integral in m of mu e, yeah, the normal at x minus the normal at y, scalar product with the normal at x, divided by the kernel, ddy, and you could wonder, why is this positive? And now, never forget the trick that Moritz told you yesterday, but very quick, a little too quick for some of them. Am I right? Yes, symmetrize this, right? We always say like this, but maybe everybody knows what it means. If I say, I take this, I symmetrize, I see right away that it's non-negative. Do everybody get it, or not everybody? I will assume that not everybody, okay? So I write this and I change. No, this I cannot do here at this level, right? I cannot do at this level, but this should be positive. I can do it at the level of the quadratic form. I can do it at the level of the quadratic form, which is symmetrizing. And then when I have double integrals, and this changes signs, this becomes a y, you do the half and half, and it becomes a square. You see what I mean, more or less, what the thing that Moritz said yesterday. This here, this is also not negative, but I don't see the reason right away. Do you see the reason why it's not negative? Quick. Oh, yes, because this is 1 minus, sorry. Oh, this is nu e and nu e is 1. 1 minus nu ex minus nu ey, sorry. x minus y and n plus. This is n plus 1 and a small n. There is no capital N. Small n plus 1 plus alpha dividend. So this clearly is not negative because it's this. And you see that here there is a principal value cancellation because at the point x, the normal will point like this. At the point y here, the normal will point like this. No, here, no, I'm thinking of another thing. No. There is of course a cancellation because when y is equal to x, this is 1. So, but it's not this 1 that I have in mind. Okay. And now, translation invariance of the equation, translation invariance of the non-local minimal surface equations implies that we will have this lemma 11 that is theorem 13.1 in CABRÉ, and the key computation, you will find it. The key computation, let me write a sentence here. The key computation to find the Jacobian, to compute, to find it, to appear in front of you, this. And it's not so complicated, it's quite simple to find? Yes, to find the Jacobi operator, the fractional Jacobi operator, the key computation in proposition 4.1. In proposition 4.1, and it's not difficult. All of them in the paper with Mateo. And I say this because the Jacobi operator was also found independently with another kind of computations by other people, by Davila Del Pino way, also before it was, no, in fact, it had already been found, the Jacobi operator, by Del Pino, Davila Del Pino way, and by five people, which is the first one. Figali, Millon, Figali, Fusco, Figali. I'll tell you some last names, and if I'm missing one, you should be able to find Fusco, Millon. No, somebody can help me?
Google.
Huh?
Google.
Who?
Google.
Well, yes. I don't know. Two more. Okay.
Massimiliano
Morini.
Maggi.
Maggi. Figali, Fusco, Maggi. And Millon. Millon is here. Because it's centered. All are centered. But Millon is the only French. So he was located. All the others are Italians. Okay. Okay, so that you should know that these papers find the Jacobi operator also. It's not so simple. Huh? I think this is the simplest way, but anyway, they are all useful. And what does it say, the lemma? The lemma of this, I didn't state the lemma yet. And the lemma says simply that the Jacobi operator on the components of any component of the normal is 0 in the minimal surface, in the non-local minimal surface, and for every index between 1 and n plus 1. Okay? This is what it says there. Okay. This will be the first ingredient to prove that. And let me tell you the next ingredients. We are almost gone with the idea, in fact, of the proof. But let me see where I have to erase. That's the gradient estimate. We have this. So let's go to here now. So now, take the last component of the normal, the n plus 1. Take the n plus 1 component of the normal. All these tricks are standard in minimal surfaces, but I'm repeating, I'm doing it now in the non-local. For instance, to take, when you have a graph, the last component of the normal is very important, it's very nice because it's positive. It's positive. You know what is the normal to a graph, right? To the graph, the last component is 1 over square root of 1 plus grad u squared. That's the last component. So this last component, mu n plus 1, is exactly, so let's take it upwards, it's exactly 1 plus gradient prime u square root, and this is positive. And now I work downstairs. Or in n. I can see it as a function of x prime, or I can see it on top of the surface. This is my choice. But I would like to see this choice, because I will have to integrate on the surface. The important thing is that it's positive. And now let's write the equation we got. Let's write the equation we got. This one. Let's forget the e. Let's forget the e. Okay? Let's forget the e because there is no. And this is the Laplace with a plus, not with a minus. The fractional Laplace, and let's change to s. We know what is s without nu n plus 1, and then c square s nu n plus 1. But this is non-negative, and this is non-negative. So this is non-negative. So all this is greater or equal than ls of nu n plus 1. So nu n plus 1 is a positive super solution of the homogeneous equation. Positive super solution because this is like Laplace, huh? This is like Laplace, so it's super harmonic. Laplace negative is super harmonic. And now you have to remember, and this is a kind of fractional Laplacian on the surface. And now you have to know your theory from Gilbert-Rödinger, the Lagrangian-Moser theory, or even first you have to learn it for the Laplace in the first chapter. Huh? That now you look at Gilbert-Rödinger at the local theory. Huh? And you have to study the Harnack inequality. And the Harnack inequality, you prove it, it has two parts. One that we call local maximum principle, because if you have a maximum principle, you localize it using a cutoff, and what you get is that, and this applies to subsolutions, and it tells you the supremum of a subsolution is less or equal than its some LP norms of it, LP norms, and maybe I have to put a positive part somewhere. Let's write it like this. I don't want to be so. That's what you have to remember in mind. And then and this is easier. And then this is easier. And then the more delicate is what we call the weak Harnack inequality. Weak Harnack inequality for super solutions. And it tells you that the infimum for super solutions or for positive super solutions? Yeah, the weak Harnack, you are going, yeah, for positive super solutions. Because if this is a super solution, if I take the infimum with something, it's also a super solution, but the infimum is still unbounded below. No, so I need to have a positive super solution. The Harnack inequality also applies to positive solutions, remember? For Harnack inequality for positive solutions. So maybe here it's better if you write a W plus or something like this, if it in case. But let's think that it's positive and here you have positive. This is the delicate. Forget about this drawing. And what does it say, the weak Harnack? The weak Harnack says that you can control the infimum of the super solution by a small constant here and some LP norms, some P that I'm not going to specify here. And I'm thinking of the homogeneous equation. If your equation is not homogeneous, then there are some forcing terms which are like some errors. But let's forget about the forcing. We don't have forcing. Well, then later we will truncate the Jacobi operator, and then it's like appears like a forcing, like a right-hand side. But this is not important. I want to give you the key ideas, and then what you have to do is to apply this. But the coefficients of this equation, this is there, but n, you don't know what it is. I mean, if you write that integrating in Rn, you are computing this. So L, if you want, if you go back to Rn, you will have to integrate on the graph. So it will be v of x prime and u of x prime, right? This is the last variable, and then no y, y. So it's not and here you will have, you see here, okay, that's fine, but here you will have x prime, u of x prime, okay, yeah, this is the key point, minus, I thought I was going to get into trouble, but fortunately I don't get into trouble. These days I'm being lucky, I'm not always so lucky. It must be you that are very nice students, and n+1 or Granada, n+1 plus alpha. And look at this, what it is, this thing down here, right? This thing down here is x prime minus y prime squared, beautiful, linear theory, quadratic, blah, 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 beautiful. But now, well, not the square root, but whatever power you have to make. This is quasi-linear. This is quasi-linear. If you don't like this, put it here, put 1, and pass dividing here x prime minus y prime. Doesn't this look like 1 plus grad u squared? Doesn't it look like, you see? In the denominator, like the minimal surface equation. So I'm in the presence of ddx, ddy, whatever, ddy probably, but I'm in the presence of a, and now the common factor, you see, I took it out. So it will be here. Oh, beautiful, this is fractional Laplacian. Beautiful, I'm integrating downstairs. Well, I have also the area measure in the numerator. There will be 1 plus grad prime u at y prime squared. Do you agree with me? Because I was integrating in M, and now I integrate downstairs. Yes? And I have this, and I have this in the denominator, pretty much. And in the numerator, I also have v, the linear part. V, which is the function v, which is here and here. But you have all this stuff. This you put with this. This is the fractional Laplacian, right, Moritz? Moritz will help us now that I don't say anything incorrect. This will be the fractional Laplacian. And then this will be like coefficients, okay? It will depend on the multiplying the kernel of the fractional, or if you want, you include in the coefficients, you include the fractional Laplacian. But you see, this is a perturbation of the thing, and of the fractional Laplacian. But still, you see, here we still don't know. We still don't know that we want to prove that the gradient is bounded. Huh? We want to prove that the gradient is bounded. We want to prove that the gradient is bounded. So we still don't know. We still don't know if these are uniformly elliptic or not. But we trust that all these will work like in the local case. And then what we are able to do with Matteo is to use. So now we run the Moser iteration technique for positive super solutions. Of this equation, in this case, L alpha or LS, L alpha or LS, that's better, LS of V less or equal than 0. We run the Moser iteration for trying to get this. And when you do the Moser iteration, you need one main thing. Two main things, but the main thing is to have a Sobolev inequality on your object on M. In this case, a fractional. In this case, a fractional, thanks to the fractional Sobolev inequality. So Moser requires a Sobolev inequality on M that we know because we proved it before, thanks to Bresis and the density estimates. So local minimal surface. And then, since you still don't know that this is uniform elliptic, you must be lucky, but this works in the local case, that the quasi-linear structure works with itself and with the LP norms and Moser, and everything goes fine. And what you get at the end, you get this proposition, and then you will see where the gradient estimate comes. Proposition 12, and this is the paper with Matteo, that says the infimum of this last component in the surface intersected with a ball. The surface is a graph, huh? And now I have a ball here, and now I have an ambient ball. Now this ball is B1. It's not prime, huh? It's n+1. The infimum of the last component, here there is the U. The infimum is greater or equal than a constant, the L1 norm. I will take P equals 1. You can take, we are able to take P equals 1, the L1 norm of the normal, ddy, and thanks to the non-locality, there is another term that is an outside contribution, outside of the unit ball, and you can put the same, but a little smaller, divided by the distance to the origin. The ambient distance to the origin is dy. This extra term is very important for us. It was realized by Joachim Serra and Xavier Ross that you can put in the non-local case that you don't have in the local case, and it helps you. So remember, in the Harnack inequality, in the non-local case, there is an extra term that helps you a little more that you don't have in the local case. This is parenthesis, is this parenthesis here. Now, is this bad or not so bad? No, this is very good, because you're integrating on the graph. You're integrating on the graph 1 over the square root. But what is integrating on the graph 1 over the square root? It's like integrating downstairs the Lebesgue measure. So this is exactly, this term is exactly here, is exactly the measure v1 prime. Do you agree with me or not? It's correct? Yes, it's correct, right? No, not exactly, because it's not the cylinder, but it's not exactly this. But pretty much it will be this, because it's not the cylinder, you know, if it was the cylinder. But what I'm trying to say is that these things you will be able to control by below nicely by the oscillation. This by the lower bound, easy lower, very easy lower bound. You will find the paper by the oscillation of the graph. Okay, in V1. And this, remember, this is the infimum of the normal is 1 over the supremum. Is 1 over the supremum of 1 plus grad prime u squared. Supremum in this piece of the surface. And you see, and this is greater or equal than that. So you are done. So now you have the gradient estimate, because the supremum of the gradient, it will be larger than something that it is of this type. So it will be smaller than the oscillation to a power. Okay.
Sorry, can I ask a little
Sure.
question?
Sure. No, it's good because
The second term in the hammer.
Yes.
How did you prove that?
That I said, it is something that that comes out as a gift.
Yes, but which technology do you use? So which tools do you use?
Nothing. Just just what you did. Just this I can tell you. Nothing else. Just cutoffs. The usual model. Cutoffs. Integration by parts and all this, and don't throw any term, but nothing.
You just observe.
Okay. Just observe that one you can keep. And that was also observed by Challenge to keep, okay? But I'm almost 99% sure that we don't use anything else. Material, but we keep it. And in fact, what we do later is to say, this is greater if I put this here. If I put here this, I'm putting something smaller than 1, so the inverse is larger than 1. No, maybe I don't remember the details, but this bound is easy. You will find it three lines in the paper. So this is the gradient bound. So we have to finish here. The next section. The next section you will see it on the scan, and you will, and then later in the future we'll have lecture notes, right? What is that, John? Let's start. If everything goes fine, but everything should go fine, I think, because this last section was the applications to mean curvature flow. So let me just tell you that with this Michael-Simon inequality, you can prove that if you have local mean curvature flow of a set, mean curvature flow, not a convex set, but who is flowing by mean curvature, and it's smooth flow and all this, you can, and you start at time 0, you can wonder yourself for bounds on the extinction time. The extinction time is the time when it collapses to a point, or when it stops being smooth. It stops being smooth. it becomes a line or something like this. And then you can find, this is called extinction time, and you can find upper bounds. There are very crude upper bounds using the diameter by the comparison principle. But there are upper bounds depending on the measure of the initial surface to a power. And this is quite simple to get just using the Michael-Simon Sobolev inequality. Okay, and you will find it here. It's just an ODE. It looks very much. No, in fact, funny, I was writing yesterday. I was like, I didn't remember this. You look at the length of this. You look at the length of these surfaces, the volume. You differentiate with respect to time. You get the integral on the surface of h squared. H is the mean curvature, because the velocity is the h squared. And you apply the Michael-Simon, and you get the volume of gamma t to the power n minus 2 over n. And we are exactly on the same ODE as in the density estimates. Exactly. Maybe with the other inequality, I don't know, but the one that works well here. You integrate it like before. There is an extinction time like before, and this extinction time tells you you cannot go more than this time because otherwise there is a contradiction. It's just the same argument. It's very funny. It's just the same argument as in the density estimates. Okay, and this, I don't know by whom it was done, but you will see a reference. First time, but you will see a reference to very nice CHIME lecture notes of Craig Evans on mean curvature flow. I wrote the reference. I hope, yes. And if not, I'm going to do it now. But I think I wrote it. And then there is the fractional version of this. But let me just finish that. As I told you yesterday, the fractional Michael-Simon Sobolev inequality in a general hypersurface with the extra term that should be some curvature is still unknown, okay? What we know is the fractional Michael-Simon on non-local minimal surface, so H alpha is 0, there is no extra term. And then with Matteo Cozzi and Giulia Zatto in Barcelona, we were able to prove the Michael-Simon fractional Sobolev inequality, but on convex surfaces, bounded or non-bounded, doesn't matter. So if M is the boundary of a convex set, then we can prove exactly like a Michael-Simon inequality here, fractional, and where instead of the minima of the mean curvature, it appears the non-local mean curvature. This didn't appear in the extra term in the non-local minimal surfaces because it was 0, but here it will not be 0, okay? But in general surfaces, it remains open. Okay, so thanks a lot for your attention. We need to take a coffee now, right? Oh, sure. Well, you were not here all week, so I forgot about this. Any question?
I wanted to ask one about the Sobolev inequality, the fractional one. And in this course, we have more for the time at an extrinsic level, and we've used from the beginning that we are in a hypersurface in Euclidean space. But Sobolev inequality is used in geometry, so I wanted to ask there is a version of this fractional Sobolev one and purely intrinsic level.
Yeah, I was thinking today because I was thinking about giving an alternative title to the lecture notes, right? Because on the non-local mean curvature is like a little generic, and I think they will let us change it perhaps. And something more precise would be, I wrote it here, Michael-Simon type Sobolev inequalities and applications to local and non-local mean curvature problems. And I said, well, this is very long, so I said, let's not write Michael-Simon type Sobolev inequalities. And I said, Sobolev inequalities. So I could have said Sobolev inequalities on hypersurfaces. Yes, but I don't like it so much. because Sobolev inequalities of there are Sobolev inequalities in the Heisenberg group, Riemannian, sub-Riemannian. There are Heisenberg inequalities. There are Sobolev inequalities. But sorry, there are Sobolev inequalities in many things, in metric spaces. There are several. So here I like to emphasize Michael Simon type Sobolev inequalities because this captures the essence of the Michael Simon, that is that the constant is universal and the only thing, all the geometry is captured in an extra term that it is the mean curvature. But of course you are asking, no, your question is very good, but you should ask more the geometers than myself. I don't know so much, but I don't think there are so many, I don't know. In a general Riemannian manifold, well, let me tell you of a conjecture, but probably that's the only, I don't know. You could think of replacing the mean curvature by some Ricci curvature or scalar curvature, things like this. Yeah. Matthew, do you know things?
Often there is a scalar curvature.
Scalar, I see. And maybe you need to make some further assumptions on the topology or maybe on the...
Often the growth volume like we did.
The volume growth. I see. Okay, let me tell you an open problem that who solved it, you are most of you under 40. Who solved it has the Fields medal. If not, I invite the person for to whatever. If not, it doesn't get the Fields medal. And of course, they are very difficult problem. The open problem is a Fields medal for sure. The open problem is that something similar to what we did here. Mendel did that the Euclidean isoperimetric inequality MV1N or something like this, okay, with a constant, okay. But this is a constant that depends only on it, okay? And it's a sharp constant, right? This inequality, Brendel has proved that it's also true for every domain in a minimal surface with the same constant Cn, right? Yes? Prove this inequality in every simply connected Cartan-Hadamard manifold. What is a Cartan-Hadamard manifold? A Cartan-Hadamard manifold is a Riemannian manifold, which is simply connected, we are going to assume, simply connected, and with non-positive curvature tensor, right? Riemannian curvature tensor, sectional curvature.
Isn't this what Gomi instructed?
Sorry?
Didn't Gomi instruct?
Yeah, but there is a mistake.
Ah.
Yeah, there is a mistake. And I heard nothing else again. I saw Yannick, who is lost. It seems that there is a mistake. So this is an open problem that, so it is, so you have one of these Cartan-Hadamard manifold, and it is believed that this inequality with this constant, it's also true for every domain on a Cartan-Hadamard manifold with the same Euclidean constant. And this is known in dimension 2. It's why I prove this. It's quite easy. In dimension, I think now it's dimension 3 and dimension 4. 4, I think also 4. Yes.
Kleiner's 3, Krook's 4.
Klein 3. First, it was proved in dimension 4 by Krook. That has a proof like that gives the right constant in dimension 4, but not in dimension 3. Like Brendel has to go 2 codimensions to get it 1 codimension 1. And then Kleiner, dimension 3. In higher dimensions, it's open, okay? And Sprague and Lee put it in archive, the solution, but I think there are some states or gaps. I don't know, I didn't ask more details, okay? For instance, if this is a geodesic ball of the Cartan-Hadamard, if this is a geodesic ball, then it's true the inequality with this constant, okay? This is known. If the Cartan-Hadamard is an homogeneous Riemannian manifold with many symmetries, then it is known, okay? But anyway, so what I mean is that this is another version that will be of Michael Simon type, of course, but here the curvature is negative. Well, I'm not very good answer to your question, but
Yeah, could you please say even shortly something about the monotonicity formula that you were talking about yesterday?
yeah, I cannot say anything else much more than what I said, that with the extension problem, it is easy to prove the monotonicity formula for non-local minimal surfaces. Caffarelli, Roquejoffre, Savin do this. It's like the same proof as the local, pretty much. But downstairs, I tried with collaborators, we tried hardly, took hard, insisted several times, several periods to prove it downstairs without the extension, and we don't know how to do it. But you can write it downstairs. Huh? You can write the statement. This quantity is monotone. Okay, is monotone in R. It's interaction. Something they are interactions.
Maybe we can thank Xavier for these nice lectures. But you always are so careful with the notes and explanations.
That's okay.
Thank you very much.
Thank you.